Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Ryan Hickox, who's a professor of astronomy at Dartmouth College, studying supermassive black holes and galaxies and how they grow over cosmic time. He is currently the chair of NASA's Physics of the Cosmos Program Analysis Group and has been engaged in the planning of multiple future NASA space observatories. Welcome, Ryan.
Hi, Gil. Thanks very much. Nice to be here.
Yeah, thanks for doing this. So I want to start with one of your older papers to sort of set the context for our conversation. So your 2013 paper, Black Hole Variability and the Star Formation-AGN Connection. Do all star-forming galaxies host an AGN? The effect of active galactic nucleus, AGN, variability on the observed connection between star formation and black hole accretion in extragalactic surveys. Recent studies have reported relatively weak correlations between observed AGN luminosities and the properties of AGN hosts, which has been interpreted to imply that there is no direct connection between AGN activity and star formation. So I guess we were using the luminosity as sort of a proxy for activity. Was that the issue?
Yeah, that's right. So the way we know how black holes grow over cosmic time. So we have a big black hole in our own Milky Way galaxy, in an object called Sagittarius A star, and it weighs about 4 million times the mass of the sun. And we think that every big galaxy around us also has a big black hole in it. You've probably seen the famous image of the big black hole in M87 that was published by the Event Horizon Telescope collaboration.
Like 4 billion solar masses or something like that?
That one is about, it's actually about 6 billion. Yeah, quite a lot larger. And so a big question had been sort of, everywhere we look, we see these black holes. Where do they come from? And there's been a lot of work over the years studying objects where these black holes are actually accreting material from the gas and dust around them in the galaxies in which they reside. Yeah. And so a quasar, which you may have heard of, is a form of active galactic nucleus. And these are objects where there's a lot of material falling onto the black hole. The black hole is actually growing. And in the process, this material heats up and radiates and produces a huge amount of luminosity. So the material, once it goes into the black hole, is gone. As you may know about black holes, that they have this sort of event horizon, and things that are inside them have no way of escaping.
Yeah.
But on the way in, the material can release a lot of radiation before it actually falls into the black hole. And this gives off a very characteristic set of signatures that we can use to find galaxies that have these growing black holes in them. And so indeed, what people have done is looked at these various signatures For example, a popular one is looking at very bright X-ray emission. Turns out galaxies are not very good at producing X-rays. They tend not to be that bright in X-rays, but a growing black hole can be very bright in X-rays. That you can then use as a way to measure what the total light output from the black hole is, and convert that then to a black hole growth rate. And so what people have done is measured this luminosity and then converted that to a black hole growth rate and said, okay, I see that one galaxy. It has a rapidly growing black hole in it because it has a lot of luminosity that I can associate with the black hole.
Yeah, but wouldn't you, I don't know much about this, Ryan, but if you look at it side on, like we would do on Milky Way as opposed to M81, head on, wouldn't you see it differently?
Yes, absolutely. And this indeed is one of the big challenges. So the sort of classic signature of a quasar, the sort of very bright objects that look, in fact, like stars in visible light, the light that we can see with our eyes. Those are ones where you can see right down to the material that's falling onto the black hole itself. And that we really see when the whole system is kind of face onto us, as you mentioned. And it's not just the galaxy, it's also the black hole has a structure around it that is kind of axisymmetric, as it were. So the material is spinning around the black hole, and if you go along the axis that it's spinning on, you don't see you can see directly to it, but in the plane, there is a lot of material building up, and there's something we call the Taurus that is something like a donut, but probably not quite like a donut. And if you're looking through the donut, then there's a lot of junk in there, as it were, that will block the light from the black hole. And likewise, if you put it in a galaxy, then now there's stuff on even much larger scales that will block some of that light as well. And so, for example, if you want to use the visible light as your tracer of how luminous the black hole is, that's not going to work if your galaxy is edge on, or if this torus on smaller scales is pointed in the wrong direction.
Yeah, I always wondered about this, Ryan, that when we look out, we are seeing all sorts of galaxies at different angles from an orientation perspective, right?
Yeah.
So to kind of have a general idea of what these things, both the content and sort of the shape of it, it's really difficult, right? Do we have sort of a mathematical way to say, if we see it this way, this is the most likely shape of it?
Yes, we do. There's a lot of interesting things you can do to reconstruct the kinematics of a galaxy, and which is the sort of motion of a galaxy, as it were. And even for nearby things, we can actually even take very high resolution images that allow us to resolve down to those internal structures that I was talking about, like this torus. And so the way that works is in particular by looking at Doppler shifts. So if you have a object that is mostly edge on to you, and then you will generally see, especially if it has some kind of coherent rotation, but you can actually tell this even if the motion is a little bit more mixed up. Then on one side, you'll see the material generally moving away from you, which manifests as a redshift of the light that you see. And if you look on the other side, you see it coming towards you, and there will be a blue shift. And so you can tell how inclined an object is by the spatial distribution of these red shifts and blue shifts. So if something's perfectly face on, you don't see any red shifts and blue shifts at all. And if something's totally edge on, then you see the strongest possible red shifts and blue shifts. And that is correlated, of course, with the shape. Like if you look at a spiral galaxy like the Milky Way, if you look at it right edge on, it kind of looks like a thin line with a bulge in the middle, sort of like a fried egg viewed on sideways. But then if you're looking at face on, of course, it looks round, and anywhere in between looks kind of like an ellipse, as it were, or an oval. And by looking at both that large scale shape and also the red shifts and blue shifts that you observe from taking spectroscopy of these galaxies, you can work out their inclination angle reasonably well, but it's not a super precise business. And a good example is my own group. It has done some observations using the Southern African Large Telescope of one of the most famous nearby growing black holes, a system called NGC 1068. And we were trying to model the actual emission that we saw from this thing. And one of the things we needed to know was this inclination. And this is, one of the very best studied objects. Like, it's super close. It's very easy to get good data from it. But even then, there was actually a significant uncertainty and degeneracy in what the inclination is. So you can partly get there, but these systems are kind of complicated, and so you're limited into how well you really can precisely do it. Typically, if you can get within, say, 10 degrees of how inclined it is, you're doing pretty well.
Yeah, I was just thinking about this, Ryan. Since Hubble and other data sources, I wondered if there is enough data to do some sort of machine learning techniques on these types of data, and train a deep learning neural networks or something like that to actually output the inclination from what it can see.
Yes. So there is it's interesting. I don't know if that sort of thing has been done for individual objects. Yeah. That's something that I know there's a lot of research in terms of developing new techniques to analyze complex systems like this. But one thing that machine learning techniques definitely get used on is larger populations of objects. So when you take a big survey of the sky and you have many, many galaxies, you need to have very good, as it were, shape parameters and some kind of information about those galaxies, things like the inclination. But often the data are kind of noisy, or the intrinsic shapes are pretty complex, and then there are things like dust lanes that can get in the way and screw up your measurements of the shape, et cetera. And so people who are doing big surveys of the sky have been developing more and more sophisticated machine learning techniques to actually get precisely those measurements. And oftentimes they don't give you a really good measurement for any individual object, but they can tell you the distribution of the various orientations and shapes much more precisely than if you were trying to just do it by hand or by eye. So that's a big kind of area of research going forward.
Yeah. And so going back to the paper, so active galactic nucleus, AGN, basically implies that some sort of a super what is the right term? Supermassive black hole, right? SP, what is it? SMBHs.
Yep. That's right.
Center of a galaxy. So we hope, or we expect most galaxies have something like that in the center. Now, my understanding, Ryan, is that the quasars are sort of the early object, right? That sort of ultimately created a galaxy around that. So if you look back in time, we could see quasars sort of naked, couldn't we?
That's a very interesting question. I think that's still actually open for debate. So we do know, based on, just to address your first point, it is true. If we look around in basically every large galaxy around us, and we look down right at the center and look at how stars are moving around in the center of the galaxy, and there's several different techniques we can use to do that, they almost all of them show evidence of a supermassive black hole. But in the vast majority of cases, they're not accreting material, and so they're not very luminous, right? So that we can't see the light from them. But as we look farther back in cosmic time, if we look at objects that are farther away, and so it's taken light longer to reach us, we see more and more of these AGN, these active galactic nuclei, that are these black holes that are giving off light as they are growing. So it's definitely true that the epoch of the growth of black holes is not today. Actually, the epoch of the growth of galaxies is not today either. Galaxies tend to be swarming stars at quite a low rate right now compared to how they did earlier in the universe. But if we look at when the universe was, say, half its current age or a third of its current age, then there was a lot more of this black hole growth activity that we see in the surveys of galaxies that we do. However, the question of what came first, the black hole or the galaxy, is still very much open to debate. And there are still a whole bunch of different theories that posit certain interactions between the growth of the black hole and the growth of a galaxy. And I really don't think that's totally settled yet. So we see, well, I don't think anyone to date has found a true sort of solitary quasar by itself that we know does not have some kind of a galaxy around it. And that, of course, would be a smoking gun for the earliest growth of black holes.
Right.
And the fact that maybe black holes do lead this process. But there's a lot of new potential observations that will help us tease this out, not only from a sort of direct observation perspective, but also in a statistical sense by observing the very first galaxies, when the universe was less than 1 billion years old, and observing looking for the evidence of the very first growing black holes as well.
Yeah. So as you look back, do we have any evidence of sort of there's any sort of size observation? So looking back, just maybe 1 billion years from Big Bang or something like that, do we see really large galaxies at that time or small?
So this is a really interesting question. So we see we see a combination. So in general, when you look in the very early universe, the galaxies are relatively small, most of them, in terms of the number of stars that they have. But we do see rare cases where the galaxies are starting to get reasonably large, meaning that they must have formed stars very, very rapidly to get that big over a relatively small amount of time. But even more so, and this is sort of getting at this point about which objects form first, we also see black holes that are very massive. Even I think the winner now is around 700 million years after the Big Bang is the sort of earliest massive black hole we see. And the way we can tell the mass of those objects is actually, it gets into this whole question about inclination and Doppler shifts, is that we look at the black hole acts sort of like a fluorescent lamp where it emits some radiation, it lights up the gas around it, and that gas is orbiting around the black hole. And so we'll have some of it will be traveling very fast in our direction, and some of it will be traveling very fast in the other direction. And so you get this observable Doppler shift in the light that you see. And how massive the black hole is determines how fast that stuff is moving. And so it tells if you see a broader emission line, which is the sort of radiation at a particular wavelength, for example, that's emitted by hydrogen that we see, the broader the Doppler shift, the larger the shift towards blue and red due to these velocities, that tells you that there's more gravity and therefore there must be a more massive object there. And we see objects well in excess of 1 billion solar masses. So that's 200 times more massive than the black hole in the Milky Way, less than 1 billion years after the Big Bang. And the problem there is that we also know that black holes can only grow so fast. If they eat material too quickly, the faster they eat, as we sort of mentioned at the very beginning, the radiation they give off is a signature of how fast they're growing. And if they're growing more rapidly, then they give off more radiation. But if they give off enough radiation, that radiation actually has a pressure that can push against the material that's falling in. And if that is larger than the gravitational pull inwards, then the black hole can't grow anymore. And so there's this sort of interplay between how massive a black hole is and how fast it can grow. The bigger ones can correspondingly grow more quickly. So if you start off small, it takes a long time to get big. because you have to, you can only grow so fast when you're relatively small, and then there's a lot of rapid growth right at the end. And if you try to work out the statistics of this exponential growth, as it were, by the way, it's interesting that in these days of COVID that a lot of people obviously have become familiar with the concept of exponential growth. But for those of us who work out black holes, that's something we think about all the time. If you'd work it out, there's no real good way for a black hole to start at a reasonable size, say, around the mass of a star, or say even up to 100 times the mass of the sun, and actually get to this really, really large mass in such a short time. And so that's a big puzzle. And there are a lot of potential solutions, including forming big black holes from scratch early in the universe. But that's definitely something that is I think one of the biggest outstanding questions in this field.
Yeah, so it keeps the field interesting.
Yes, absolutely.
So in the 2013 paper, you sort of posed the question, the AGN luminosity, whether that is really correlated with activity or inactivity. And you said the results provide motivation for future deep, wide extragalactic surveys that can measure the distribution of AGN emission rates. And you have a recent paper, and your hypothesis, perhaps a bit more advanced now, obscured active galactic nuclei, AGN, are powered by the accretion of material into a supermassive black hole and are among the most luminous objects in the universe. However, the huge radiative power of the most AGN cannot be seen directly, and is hidden behind gas and dust. And so this is really what a good part of the work that you're doing now.
That's right, is looking at these heavily obscured sources where it's hard to see all that luminosity. And so, that in that 2013 paper, I think it was ultimately published in 2014, the argument we were making there was that when we compute the black hole growth rates using these observed luminosities that we see, we needed to be really careful about how we interpret that. Because instantaneously, we do expect that if a black hole is growing right now, today, at a certain rate, it probably should be giving off a certain amount of luminosity that's ultimately proportional to, the amount of mass that's falling in. The problem was that people had, for a long time, interpreted that to identify a particular class of galaxies that had these growing black holes in them, and asked the question, why do some galaxies have these growing black holes in them? Why are those black holes growing? And other ones, I look at some other set of galaxies, and they're not growing. And so there'd been this big industry, once people started being able to do surveys to detect lots of these things, to try to actually find what is the key about a galaxy that actually makes its black hole grow. And I like to say that the history of that was a history of tantalizing 1 sigma results, where people were expecting to see something but didn't really ever see anything definitive. In other words, the galaxies that didn't have black holes in them that were growing were basically just like the ones where the black holes were growing. And so that paper made we sort of made the observation, and there was a lot of evidence by many other groups that we kind of put together for this, that the black holes probably, when they turn on and start growing, they maybe don't stay on for that long. And actually, maybe they, rather than just turning on and off like a light bulb, maybe they flicker all over the place. And sometimes they're growing 100 times more rapidly, and sometimes they're growing 1,000 times less rapidly. And they go over many orders of magnitude in terms of how much they grow, and they can do that in millions of years, which for the time scale of a galaxy is a very short time. And so the hypothesis that we said was, well, wait a second, maybe all galaxies, including our Milky Way galaxy, are actually growing their black holes in some relatively well-behaved average sense. But then it's flickering all over the place because of a lot of complex physics that happens around the black hole itself, where you have this radiation that we talked about before that can drive material out if it suddenly gets too luminous, or the gas flows in, can get unstable and fragment, and all kinds of things can happen that will cause the black hole growth rate to vary a lot. And so we maybe were thinking about this all wrong, that you wouldn't actually expect there to be a difference between the black holes, the galaxies that are growing their black holes and the ones that are not, because actually all of them, maybe at least the ones that have a gas supply that the black hole can actually eat, maybe all of them on average are doing that. And in fact, in our own Milky Way, we see evidence for remnant structures. There are these big bubbles of high energy material above and below the Milky Way called the Fermi bubbles, that may have been actually produced by an outburst from our black hole, on the order of millions of years ago. And there's actually evidence for even more recent outbursts than that were kind of smaller scale ones. So I think now that picture, it was interesting. We've kind of been moving towards it in the field for a long time until 2013, 2014. But now that sort of statistical picture where you have to treat this as really look at the whole distribution of growth rates, because you can't, these timescales are long enough that no astronomer can sit there and watch a galaxy and watch its black hole growth rate vary on the scale that it would be for a million years. We actually do see a handful of, and this is an exciting new discovery, a handful of objects that do change in their growth rates on something like years of time scales, which was not expected. These are what are called changing look objects, and they're a very exciting area of research. But in general, you wouldn't expect to actually be able to watch a single system go through this whole cycle. And so what we need to do is instead, and this is getting at the future prospects, is to observe a lot of galaxies, measure the accretion rates in a lot of galaxies, and then use that to statistically understand what is that distribution and how does that match into what we would expect from these statistical models of black hole growth.
So if I understand this correctly, Ryan, your hypothesis actually makes if I understand correctly, it makes a lot of intuitive sense. So are you saying that black hole growth is sort of more uniform wherever black holes are found? It's not like they're feeding and they're going to sleep and they come back on. There is a process that can be more universally defined, but the data we are picking up is really hidden, as you say, behind gas and dust that's moving. So we might pick up flickering and other type of things, but that is just sort of the perspective problem. Is that what you're saying?
It's interesting. There's two biases involved here that make it hard for us to see the whole picture. So you're exactly right that we as astronomers, when we take our picture, we have two problems. One is that we are observing its galaxy at a very specific time, which is the time that its light is reaching us. And we are observing it from a very specific orientation, which is where the Earth is. We can't fly over to the top of the galaxy and look down on it from a different direction. And so the timescale one is the issue about all this flickering that I described, and that what you see is in terms of how it's growing right now may not be a good indicator of how long it's been growing over the last 10 million years or something. But there's also the issue of them being hidden behind gas and dust, and this is kind of related, but also a little bit distinct, and it gets back to the question you asked early on about about what happens when you look at one of these things. John, when you're looking through gas and dust, a lot of the signatures that we would normally expect to see, like ultraviolet radiation and optical radiation and even some kind of infrared radiation, those all get absorbed by the gas and the dust. And other signatures like mid-infrared or radio or hard X-ray emission are things that actually penetrate. So we use hard X-rays, high energy X-rays, when we take an X-ray of your hand, or same thing. And so those can penetrate through this obscuring gas and dust. And actually piecing that all together turns out to be quite a lot more complicated than you might expect. And so they're probably, I think, there are the latest conclusion, and one of my graduate students has just published a paper, the one you were referring to, Gil, about this, is that we think there's actually a large population of these really quite heavily buried AGN that we didn't know about before, and so or at least we didn't have incontrovertible evidence that those objects really were growing black holes. And so, yeah, in order to piece together the whole picture, people talk about as doing a cosmic census, right, where we're trying to actually add up all the black hole growth because we want to know where ultimately the black holes came from. You have to think about it both in terms of how things change with time and also how things change depending on the configuration and the orientation of the material, and that both of those, are the things we're continually making progress on.
Yeah, so the paper that you mentioned just now, the more recent paper, a large population of luminous AGN lacking X-ray detections for heavy obscuration. So don't X-rays penetrate through the gas? So how do I understand this? So these are luminous active AGNs, luminous AGNs, but they don't have any X-ray detections.
So they, that's a good question. So X-rays do penetrate, but they don't penetrate perfectly, and they especially don't penetrate very, very large amounts of material. So if you were going to look, the X-rays have long been considered to be a really good way of finding these buried growing black holes, because compared to the traditional optical methods, the X-rays penetrate very well. But once you get up to really high, what we call the column density, the sort of like amount of stuff along your line of sight, actually even X-rays can get scattered by the electrons in the material and will not make it towards your detector very well. And most of the sensitive telescopes we use are relatively low energy X-rays that are more easily scattered by this material than higher energy X-rays, or more easily absorbed, as it were, than the higher energy ones. And so what in this paper, we were looking mostly at those objects. So most of the constraints came in the lower energy X-rays. And we found objects where the mid-infrared signatures, it turns out that in the sort of longer infrared wavelengths, they're less affected by this obscuring material. And also they're actually sort of complicated, but the geometry in which the infrared light is emitted is a little farther out. So some of it actually doesn't intercept the obscuring material at all. So we use the infrared signatures to say, hey, there's a growing black hole in that galaxy. And then say, okay, if it were not obscured by anything, I would expect the X-rays to be really bright. And you go and look at the particular object, and not only is there, for many of them, is the X-ray, not only are the X-rays faint, they're actually not detected at all in the images. And so we did and my graduate student, Chris Carroll in particular, did a detailed statistical study of this, where he tried to work out how much obscuration do you actually need to have in order to have not seen these things. And it turns out it's a lot. And so they're sort of on the high end of how buried we expect growing black holes to be. But then we also did one thing. We said, well, how sure are these things that they're actually growing black holes at all? Could this just be that the infrared signatures were getting this wrong and they're actually something else? And so one thing we did, which is a really cool technique that my group and a number of others have developed, is we used what we call stacking, where you can take a lot of images of objects where you think there might be some emission. In this case, it would be X-ray emission at the position of some object. And if you go and look in the X-ray image, it's kind of noisy. You can't see anything there.
Yeah.
But if you take, say, 100 of them and you add all those images together, then the signal will start to pop out above the noise, and you can actually see a little point source in the center. You couldn't have detected any of them individually. It's like taking a whole bunch of short exposure photographs and then adding them together. And so when we did that, we actually saw that the X-ray emission was faint, but it was more than you would expect for just a regular galaxy. So that was giving us some good confidence that the system was, these systems really do have growing black holes in them, but those black holes are buried behind a whole lot of gas and dust.
Yeah, so two different things, right? So the first idea, if I understand this correctly, Ryan, so these are AGNs potentially obscured by dust and gas, but you can see them in infrared. I would imagine they're not very luminous in visible light, right? But
Yep,
you see
right.
them in infrared, and you expect, because of the infrared intensity, you expect X-ray intensity too, but you don't see the X-rays from that. And then you're saying if you stack the X-ray picture, so to speak, you can actually recognize what's at the center. So this appears to be sort of a good way to test your hypothesis, right?
Yes, absolutely. So the X-rays are a good way of confirming that we have growing black holes there, but also these stacking techniques, as it were, also, if it's what you're getting at, also help us test this other hypothesis about the flickering variability, because what that tells you is that there should be a whole bunch of galaxies whose AGN luminosities are kind of just below the threshold of being able to detect them in the observations that we have. But if you add everything together, then you can see the signatures of that. And indeed, there's actually been some great work by a number of groups, some of them working in the very deep observations with the Chandra X-ray Observatory, like the Chandra Deep Field South and the Cosmos Observatory, or Cosmos Field, excuse me, where they've taken very deep observations of a small patch of sky, and then sort of statistically done this kind of work and asking, is there this residual black hole growth in there that we did not detect as individual sources? And lately, there's been really cool work from this. It's basically all of this is now both confirming, but also kind of adopting this particular picture that I was talking about the broad distribution of accretion rates and the kind of the flickering behavior. And they find really neat relationships between things like the star formation rate, the mass of stars, and in particular, the morphology of the galaxy, whether it's like a dense, compact thing or whether it's something that's more spread out, and how fast the black holes are growing on average. And so this stacking technique has become really powerful in trying to sort of push forward this whole picture.
Yeah, it sounds very foundational, right? Unless we get this right, any ideas we may have in on star formation and other phenomena, we're going to get it wrong, though, right? I mean, unless we get this part right.
Yes,
pretty well.
That's right. So yeah, it's easy to confuse these things. And so there's a vast literature of people, working out various diagnostics to really understand what the different processes we see. And one thing I should point out is that in most of the galaxies that we do this kind of work in, they're far enough away that if you take an infrared or an X-ray observation, you're not seeing the resolution is not high enough. The sort of spatial, clarity of the images is not high enough that you can say, oh, I'm looking right at the center, or I'm looking at, you're basically just looking at a smudge that's all the light that's coming from the whole galaxy. And so, we know, for example, that star formation produces a significant amount of infrared emission as well. And so if you're just looking at a blob and all you have is the sort of colors of that blob in different wavelengths, you have to be really careful and really sophisticated in terms of how you actually figure out what's going on.
Yeah. So do we have a way to sort of look at the fingerprint of emissions from a black hole as opposed to stars in a galaxy when we look at
Yeah,
an image?
and so that really is an area of a lot of continuing work. It's easier if you have a galaxy that's nearby where you actually can zoom down to the center, because then
Yeah.
you're not worried about most of the light from the stars and all the other stuff in the galaxy, right? You're just looking at trying to tease out the emission you see from very close in. But if you're looking at an object that's farther away, where you can't really do that, sort of spatial distinction, and all you're doing is just adding up light from the whole system, then there are some characteristic features of the light that we can use to tell these things apart. And so one of them, as I mentioned, was the X-rays. Just X-ray luminosity by itself is sometimes enough to tell you, because stellar processes just don't produce very large luminosities of X-rays. So if the thing is just booming bright in the X-rays, you can be pretty sure that you know what you're looking at. In the visible light, if you can see, so if you have one of these unobscured things like a quasar, in the visible light, if there's a lot of very, very blue light corresponding to the hot sort of 100,000 degree emission from the disk of material right around the black hole, that looks a lot different than stars, because stars, the hottest stars can get are several times less hot than that. So you have, or at least a few times less hot than that. So you have that particular kind of temperature signature tells you something in the visible light. You can also see, I talked about the gas, it being like a fluorescent lamp. Turns out this really hot disk produces a different set of emission lines. So different elements in the gas actually fluoresce differently depending on whether they are lit up by a black hole, this very hot disk of material around a black hole, or by stars. And so that's another way of telling the difference. And then the one that we've been using is in the infrared, has to do with, again, temperature, and it's the temperature of the dust. So typically stars form inside of dusty clouds, and they heat up that dust to a particular temperature, and that radiates. But also there's this dusty material in this Taurus and this other stuff around the black hole in an active galactic nucleus, and that's getting blasted by this radiation from right around the black hole, and that heats up to a higher temperature, sort of thousands of degrees, as opposed to tens or hundreds of degrees. And so once you get to thousands of degrees, again, the sort of typical shape of the typical colors in the infrared look different. And we therefore have ways of trying to sort of look at those colors and piece things apart. But the real trick comes when you try to model the whole thing all at once. You use the data from the X-rays, you use the data from the optical and in the infrared, and you try to kind of make a coherent picture of the whole spectrum, as it were, of the galaxy, and ask, is that more consistent with it being a star formation, or just a regular star-forming galaxy, or do we really need a black hole in there to explain what's going on? And so that's the kind of state of the art, and that's something that our group has done a lot of work on.
Yeah, I'm obviously biased about this, Ryan, but I again see some opportunities for machine learning here. Sort of unsupervised machine learning, right? You can find patterns, and what you're describing is sort of a pattern in temperature, a pattern in radiation, and if you can find similarities there. I remember seeing. Maybe this is a very early part of the quasar. Don't they create some jets sort of perpendicular to the galactic planes, or that is just very few of the quasars?
That's a great question, Gil. So that's a relatively small fraction of the quasars. It's only about 10% of them that make these relativistic jets that in particular you see in the radio. They produce something called Synchrotron Emission, which is caused by electrons spinning around in a magnetic field line, and that actually makes quite luminous radio emission. And you can see these amazing sort of thin jets of material coming out from these galaxies that goes over hundreds of thousands of light years, even out from the center. And so that's one signature, by the way. If you see that, you know for sure that there's a growing black hole there, because there's no way stars could make something like that. And so there has been some work about trying to, identify those things and also sort of characterize them. But there also is, and there, to be fair, there's actually a fair amount of work that uses the optical and infrared colors to try to separate these things out using machine learning, as you mentioned. So there has been, we've been kind of moving into a regime, and as you probably know in astrophysics, we're getting more and more data all the time, and we have big projects like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope that are going to produce just massive amounts of data, and we need really machine learning techniques to be able to interpret all that. So kind of leading up to that, people have started to develop some machine learning techniques about how to tease out the AGN emission from the star formation, for example. I think that the thing that makes it hard is that in a lot of these objects, we don't actually know for sure what the growing black hole should look like. And so you can start to see the patterns, but on the edges where it's most interesting, we don't have the kind of the sort of truth data set, as it were, that we can always compare things against. And I think that makes things a little bit difficult. But definitely that's where the field is going in the future.
Yeah. We'll take a quick break, Ryan. When we come back, we'll talk more about the cosmic evolution of the supermassive black holes.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back. Ryan, we were talking about AGNs, Active Galactic Nuclei, and the variability that we see in them, what that implies, what might be causing them, perhaps dust and gas and other aspects of the galaxy. And you're doing a lot of work in this area to tease that out through observations of various types of radiation from galaxies. You have another paper, Cosmic Evolution of Supermassive Black Holes, a view into the next 2 decades. You say the discoveries made over the last 20 years by Chandra and XMM Newton surveys in conjunction with multi-wavelength imaging and spectroscopic data available in the same fields have significantly changed the view of the supermassive black hole and galaxy connection. As we discussed a little bit, there's a chicken and egg problem here, which came first. And if you solve that, it's still unclear how it all happened, right? So what's our sort of the best current understanding of the connection between supermassive black hole and the galaxy?
This is the sort of $1 million question, Gil. I think this is what we all want to know. I think our best understanding of this connection, the simplest one, is in a lot of ways also the least interesting one, but it gives us a kind of starting point to begin with, which is that we have a good sense of how galaxies form in the universe. They form through the collapse of cosmic structures. So the regions in the very early universe that are the densest, they form into these big halos of dark matter that you may have heard about, and then inside these dark matter structures, the galaxies form. And the processes that cause galaxies to form, and in particular the ones that make them grow quickly, are also things that can funnel a lot of material down to the center of the galaxy and cause a black hole to grow at a relatively rapid rate as well. And so the sort of more gravity you have and the more gas you have, the more the black holes will grow on average. That's not a super enlightening picture, but it basically tells you that the bigger black holes, or the bigger galaxies, excuse me, have bigger black holes in them because there's this just overall connection, and the bigger things grew early in the universe and they grew rapidly in the universe.
And there is, very simplistic, there's more material.
Yes.
That the black hole can grow from, right?
That's right. There's more material and there's more gravity as well, which helps pull that material down in towards the center of the galaxy. Exactly how you do that is complicated because most material in a galaxy just wants to go around in a big circle. It's not actually, you need some process to give it a torque, as it were, and actually drive it down towards the center of the galaxy. Some tiny fraction of the rotational motion of the material is left by the time it gets down onto the black hole. But in general, just to, all those details aside, basically you have more gravity, you have more mass, and so more material to fall on. So yeah, you get a bigger black hole. I think the details, though, are really interesting and are still very much open for debate. And so there's a lot of questions like, what impact does the growing black hole actually have on the gas in the galaxy? So we talked about this radiation that the black hole produces, and they can really be very luminous. A typical black hole, this is a fun exercise that I do in my introductory classes, is that the total amount of energy per second given off by a black hole is equivalent to 10 hydrogen bombs for every grain of sand on the surface of the Earth every second. And that huge amount of just energy getting input will have a big impact on the material around it. You could just do very simple arguments to show that if some of that stuff gets absorbed by the material, it will either blow it out of the galaxy or it'll heat it up so much that it'll change state and potentially, not form into new stars. And so there is definitely a way in which if you start a black hole growing in a galaxy, it can have a big impact on the subsequent evolution of that galaxy by changing the gas content and changing the state of the gas. So that's exactly how that works. Yeah. When do the black holes grow, and when are they mostly eating, and when does this feedback instead sort of have a big impact on the star formation? Is still a big area of both theoretical and observational inquiry.
So we cannot answer this question, right? Is a supermassive black hole a necessary condition for galaxy formation? We cannot answer that question yet.
That's a great question. I think it depends on the mass of the galaxy. We definitely know that there are lower mass galaxies and some, perfectly spiral galaxies that only have a disk. They don't have a little bulge of material in the center. There are definitely some of those where people have done very, very deep observations looking for the gravitational signature of a black hole in there and have not found one. And so I think it's fair to say that some galaxies can definitely form without a massive black hole at the center. Whether or not...
So if that is true, couldn't we then extend that to say, we know, like you said, we know how a black hole could grow over time by pulling in materials. So if we're finding galaxies without a black hole, couldn't we then reasonably assume that the galaxies form first? Or we don't...
Well, yes. So I think it's interesting. So I think that in any reasonable scenario, once the black holes start getting pretty massive, they pretty much have to have a galaxy around them, right? Yeah. Because the supply of material that's going into the black hole is also forming stars, and there's got to be some symbiosis there once they start getting pretty massive. But it's a really interesting question, and this gets to sort of some of the really exciting stuff for the future. There's a really interesting question about what happens in the very early universe.
Yeah.
So I mentioned this this problem that if you look at the most massive black holes, there wasn't enough time in the universe for them to form from a small black hole. And we know, by the way, when we ask how black holes originate, we know there's for sure one way that they can happen, which is that a massive star reaches the end of its life, blows up, and the core collapses into a black hole. And so that can give you a black hole of sort of tens of times, maybe 100 times the mass of the sun. From the very most massive stars could potentially produce a black hole like that. But if you take a black hole of that mass, it can't grow using the standard methods that we think about in processes into one of these really massive ones. Early in the universe, there's just not enough time. And so another possibility, people have proposed a bunch of different potential sort of avenues for this. But one possibility is that the black holes don't actually start out that small. They start out significantly more massive, like 10,000 or 100,000 times the mass of the sun. And the way it's been proposed for that to work, there's kind of a fine tuning in the physics that you need in order to actually allow that to happen. But the idea is that in the very early universe, you may have an overdensity of this dark matter, and inside of that have a sort of pristine cloud of gas. And under exactly the right conditions, that whole gas cloud all at once can become unstable and just fall down into a black hole. That can be massive. It can be 10,000 times the mass of the sun or so. And so there, if you're talking now, 10,000 times the mass of the sun, not a million or a billion times the mass of the sun, this picture is predicting indeed that you have a black hole with no real galaxy around it, or at least a galaxy that has not formed very much before then. And ultimately, this halo of dark matter will grow. It'll collect more material, and the galaxy will kind of form around this black hole, which then can start growing from this higher mass and eventually get up to the very high masses that we see. And so that's one prediction. The problem is that with black holes, they don't leave any evidence they don't contain any evidence of how they formed, or at least not very much evidence. So if you look at galaxies, we have the equivalent of the fossil record in galaxies, and people actually call it galactic archaeology, where the stars, old stars, the ones that formed early in the universe, are still there, right, in galaxies when they formed. And so you can look at our Milky Way, and you can look at the ages of all the different stars and actually piece together its history. Whereas for black holes are the simplest objects in the universe. The only properties they have are a mass, a spin, and maybe an electric charge, but they actually, astrophysical black holes, we don't think have any charge to them. So that's not very much information, right? So if a black hole formed and all you can observe is its mass and its spin, you don't really know. And most of the time, by the way, spin is hard to measure, how fast they're rotating. Most of the time, you can only measure their mass. How exactly where that came from is really hard to say. So by the time you get to more nearby to us in the universe, at later cosmic times, the history of those black holes is mostly erased, and we don't have any way of telling whether they started out as a 100 solar mass object or a 10,000 solar mass object. So one of the best ways to observe this is to actually watch those systems growing in the first place.
Right. Yeah, so lot of complications. So that 10 to 100 solar masses, we sort of know how those form. About 10,000 solar masses, there are multiple conjectures, as we discussed. And then the gap between these two, there are other complications there too, right? Do we know how the intermediate size, do they exist?
Yeah, that's another $1 million question. I really don't think we know. I mean, there's been a lot of exciting work on this, and there have been a number of candidates, but I think, in between sort of 10,000 to 100,000 solar masses, there's some pretty good evidence for black holes like that. But of order 1,000 solar masses, we still, I don't think, have any really robust measurements of a black hole of that mass. There are some candidates, and there's some sort of, I think, preliminary evidence. But right now, we don't know whether those things do exist, and indeed, how would they form? Well, it depends on sort of how, I think, to a large extent, how these processes happen in the early universe that we talked about. Like, I think it's challenging to form 1,000 solar mass black hole through this direct collapse technique. But if you had 100 solar mass black hole that formed, it wouldn't be that hard to grow that 100 solar mass one into 1,000 solar mass one. But then you would need something to stop its growth and have it shut off, and that's also a little bit difficult. So yeah, if we ever were to find one of those, I think it would present a really interesting puzzle.
Yeah, I was thinking, right, if I were a young graduate student, this is an area to go into because there's going to be job security here.
Yeah, especially with not only new observations like the X-ray telescopes that we're thinking at for the future that would be able to observe these black holes growing and emitting radiation, but you may have also heard of I'm sure you know about LIGO, the Laser Interferometric Gravitational Wave Observatory, that's actually found black holes merging. And in the sort of farther into the future, there will be a space instrument called the Laser Interferometric Space Antenna, or LISA, that will be able to do that same stuff for now supermassive scale black holes. And so not only will we be able to see them growing in one way, you can actually there are multiple avenues in which you can see them get bigger. Because one thing I didn't mention is that a whole nother growth channel is just for black holes to just merge together with each other and keep getting bigger. So yeah, the future of this, especially getting into the 2030s or so, is really, really exciting. And I think history tells us we don't really know, like we can expect we know what we're going to see, but then we're going to find something that nobody expected, which is even more exciting.
Yeah, I know Lisa sort of LIGO in space, looking for a slightly different scale. So in conclusion, Ryan, what do you think in this paper? You're kind of thinking about next 20 years. Where do you think we will make the biggest leaps in this area, if you were to speculate?
I'd say there's probably 3 avenues that will make the biggest progress on. One of them is kind of mundane but really important, and that's just statistics, in the sense that we talked before about how black hole growth is a statistical process, is a sort of stochastic process, as it were. And so we need to have a large number of objects to be able to actually tell what's going on. And that way, it's kind of like doing a trial of a vaccine, right? You need to have enough people in there that you can build up the signal to noise that you need. And there are a lot of exciting observatories. I mentioned a couple of the ground-based and space-based optical observatories, but there are also new X-ray observatories and potentially infrared observatories that will give us wide field coverage and give us millions and millions, not billions, of galaxies that we can begin to do a lot of this work with. So that's one area that I think, one scope of progress, which is that we've previously been limited by small statistical samples, and that's going to change in the next decade, really. I think the next progress will come, or another big area of progress is in the form of theoretical understanding. So there's obviously computers improve all the time, and a lot of the intuition that we get for what we observe for these objects is based on computer simulations that handle a lot of the really complex physics that we're talking about. And one of the big challenges with this particular work is that it's been very hard to model both the small scale of a black hole, because one thing to keep in mind is that black holes are, even these big, massive black holes are actually tiny compared to the size of their galaxy.
Yeah.
And so it's very hard to model a whole galaxy and the black hole down in the center at once. But there had been recently some breakthroughs in this area where people are starting to be able to use clever, A, big, powerful computers, and B, clever techniques to actually span that, dynamic range and scale. And so I think that will be a big area of progress, is a sort of more complete theoretical picture. And then lastly, I think the biggest one and the most exciting one, getting back what we were just talking about, is the ability to actually observe the growth of black holes in the very, very early universe, either directly through the emission from X-rays, for example. So there's a mission that has been proposed to NASA and is being considered right now called LINX, which would give us the deepest X-ray images ever seen, and we'd be able to see a 10,000 solar mass black hole when the universe was only a few 100 million years old. And so that, if we're able to do that, that would be really exciting. And then also LISA will similarly allow us to observe the merging of black holes directly in the very early universe. And that, I think, is going to really help nail down this sort of origin story that we're all trying to piece together. So it's exciting.
Yeah, this has been great, Ryan. Thanks so much for spending time with me.
Oh, my pleasure. Thanks, Gil. This has been fun.
Thank you.
Bye now.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.